ice cream into the shell without any waste or without lack of product, because both things, the first thing may be the manufacturer unhappy, and the second thing may be the customer unhappy. So everybody wants to be happy, so we have to maximize the yield of it. So the strategy is pretty much the same. Here the calibration is much easy, and also the specifications were much more relaxed here. So only 2% was required here. We used 2D cameras because the speed was not really an issue. We used also the peak detector tool in software, the merger tool, and the metric calibration tool. So the setup is quite straightforward. We have 2 cameras looking at the laser from opposite sides. So we see, with the same camera, we see the coconut shell from one side and from the other side. What we are doing with the merger is the left view and the right view compensate each other, so that at one side, in this side, you see there is no data. There's no data because there's an occlusion. On the other side, in the same place, looking at it from the other camera, we have data. So that we merge the two, and the result is that we have data there. So we can use that data to compute the volume. The calibration of the system is very straightforward. The coconuts are supposed to be put on top of a conveyor belt and progress along the conveyor belt. So the calibration is using the very standard object here. So you just scan it as though it was a coconut, and then the system is calibrated with very high accuracy. So for you to see how it is, it's just progressing. After the acquisition, we get this, and because we already know the relationship between the laser coordinates and the effective manufacturing of the object, actually we know which are the coordinates of the vertices. Then we can put them in correspondence, and we get the system calibrated automatically without any interaction of the user. So actually there's no problem at all. The strategy of computing the volume is exactly the same. So we have to reconstruct virtual slices of the coconut, integrate the values within the stripes. Then we have areas, and again, by adding up areas, so by integrating the areas, we have the full volume. And by having the full volume, we have one of the data required. One of them was to have the volume, the inner volume, and the other one is to have other parameters like the length and the width of the coconut in the same machine. After the volume is computed, there is an automatic sorting system that uses pneumatic pistons to push the coconuts and classify them according to the volume, so that there are different boxes corresponding to different volumes, so that the customer can program the filling machine with different values, with a really minimized waste of the ice cream. So again, summarizing, it's exactly the same approach here. Shell coconuts are still a natural product by fortune. So all of them have different volumes. There's no two are equal. So we must compute the slices of each one. So this is a product that must be computed 100% of them. And since we also are accurate at estimating the slices, and so this means that actually the yield is really minimized. So this is a summary of the two applications. I think we've been pretty sharp, but 5 minutes left for any questions you may have. Thank you very much for your attention. Sure. Is there a question? With the overlap of the area computation. Oh, that's what the area computation does internally. No, actually, you know which points correspond to each one. So you have all the points in the same coordinate system. You can sort the points if you like, in some way. When, for example, by the angle. Yeah. Yeah, it still works. That depends on the field of view. But if it's huge, then putting an extra camera is not a problem. You just design with 4 objects and it still works. 5 cameras, N cameras. Yeah. Okay, thanks.